We're going to work as a team because we've brought back 1,000 kilos.
Oh my!
Yeah.
A ton.
Yeah.
A ton of.
You brought back a ton of rock from Antarctica.
We had a
I guess at the
permit
scale of a continent, a ton is not a huge amount of rock.
For a
but-
helicopter.
for a helicopter. I know. We had a permit for 1,000 kilos and I really didn't think we'd get there, but we did.
Well done.
Hello and welcome to Wonder, the People Planet podcast brought to you by Geo Co. I'm Holly Cooke, joined as always by my colleague Dr Anthony Reid. And Anthony and I have the absolute pleasure of sitting opposite a modern-day Antarctic explorer. We've got Dr Jacqueline Halpin from University of Tasmania. So let's get into some Antarctic science. Jacqueline, lovely to have you on.
I heard that Antarctica is about 1.5 times the size of Australia, but it's way down the end of the Earth. It's on the South Pole. What's so important about it?
Yeah, good question. It's a huge continent. And I guess it's one of those places that's really special because it's put aside for science and peace. And it really is a workhorse in terms of modulating our climate as well. So it's a special place. There's a lot of unknowns and a really important part of our kind of global system in terms of what keeps our planet healthy and at the right sort of thermostat.
Yeah.
So a very important spot.
So there's social things in terms of peace. Like that's really interesting as well. So in what sense is it a zone of peace? What's the deal with that?
Yeah, so there's an agreement between nations that this continent is set aside for cooperation, collaboration and science, which is pretty special.
It is special.
On that kind of global platform.
Absolutely.
That nations are signed up to that. So yeah, there's definitely an ethos of collaboration there with different nations working together on science projects.
Different nations have their own bases down there. And in that sense, collaboration, people are happy to cross the different... Do you need a visa to get to different bases?
Yeah, so you need to take your passport, definitely.
Okay.
And what's pretty cute is each of the stations have stamps. So you can stamp your passport, but it's not official, right? But everyone wants a stamp.
Collecting.
Penguin. Yeah. So yeah, nations have bases, not all nations, but quite a few nations have interest in the region, have bases. Australia has 3 bases on the continent. And yeah, there is that ethos of collaboration. So scientists moving between stations, working on projects together. We had, for example, the French team at Casey when I was there recently who'd come out of their base and were transiting through, and the Chinese team were coming shortly. So, yeah, so it's a very international place to be.
On the contrary, even though you said it wasn't official, I love the idea of scientists running around Antarctica just stamping passports in the spirit of collaboration. And
you should have seen the level of excitement of the stamps when the stamps come out.
Really?
Oh my God, yeah.
Excellent. I've always, when I think of Antarctica, like as a kid growing up, I just think of a big ice at the bottom of the earth and not like unchanging. I mean, you get ice falling off into the ocean and whatever, but really just this static big blob of ice that sits at the bottom of the earth. And then when you go on Google Earth, it's like this weird white line at the bottom of the page because Earth's circle and it can't be represented. But it's not unchanging. Just on the brief, we caught up for coffee this morning, even just the brief chats with you, Antarctica is not this static thing that sits there and has always been and always will. And not even just in a climate change sense. We know that we're, warming temperatures will melt ice, but not just unchanging in that sense. It's a continent and continents change. Does that ring a bell with your research?
Yeah, for sure. So the modern Antarctic continent, from a geological sense, that's kind of a recent scenario, right?
Wait. Recent?
He's got a beef with
time.
He's got a beef with time.
Just drop in there. Sorry.
Yeah.
How long ago?
Well, the modern Antarctic continent is really, we had to break Gondwana up to form that modern continent that we know today, that we see on maps. So really, the last 100 million years, probably a bit less than that, 50 million years is the modern continent that we would recognise in terms of its outline. Obviously, the ice sheets have been shaping it since then, since about 30 million years ago as well, been shaping it, eroding it and changing the landscape. But prior to Gondwana, bits of Antarctica were connected to all sorts of different continents. So, yeah, if we go further back in time, we can break Antarctica up and put bits of it with India and Australia and South America, for example.
Amazing.
So I heard that there's a rock. If you go to the southern part of Eyre Peninsula, there's a rock there that looks kind of, it's very characteristic. It's just a rock that sticks out into the ocean, basically on the edge of the continent,
On
right?
the edge of Australia.
But I heard that there's a rock that looks exactly the same on the outcrop way down in Antarctica on the other side of the ocean. Is that the sort of thing you're talking about, piecing those things together?
Yeah, so to go back in time, that's what we can do, is piece those geological piercing points, for example, back together and sort of undo that those ancient ocean basins that have opened up since then. So that particular rock, the phyllite, I think you've probably seen it. I haven't been to that location in South Australia, but really famous location, and it lines up with an outcrop at Cape Hunter in Antarctica, which was discovered by Frank Stillwell when the Australians were first there in the early 1900s. And I think that's a fabulous location because I think it's a very distinct type of rock. It really sticks out.
Yeah, it is unusual.
Yeah.
Even in the southern part of South Australia here, mostly you see granites or gneisses, these sort of higher grade metamorphic rocks. And this thing is really unusual in that context. So did Frank Stillwell know about the South Australian rock type at that time?
I'm not sure, actually. He definitely recorded his observations when he was based at Cape Denison nearby. But the correlation, I think that may have come a bit later. Yeah. So that's a cool spot because, well, it's geology, and because I think it's not a very wide outcrop, so it's maybe a couple of kilometres wide. So when you're piecing something together that's narrow like that, you can really make a very precise correlation and line up Australia and Antarctica back in time.
That's unreal. So just to be really clear for any non-geologists playing along, there's a point in South Australia where you can have one hand on the rock and one out pointing into the Southern Ocean and know that millions of years ago you would have been looking at Antarctica, right? Your next footstep would have been on Antarctica rather than into an ocean.
Yeah, that's right.
Unreal.
Yeah, so Australia and Antarctica started to break up about 84 million years ago from the west to the east. It sort of unzipped. So gradually worked its way east. And those rocks would have been contiguous probably since the Paleoproterozoic, so over 1.6, 1.7 billion years ago is when they formed and lived happily together and then split apart about 80 million years ago.
Oh my God. But so I'm here dreaming of like a footstep on Antarctica.
Yeah.
But maybe what we haven't made clear yet is you've many a times and very recently actually been exploring Antarctica.
Yeah, I've just come back from a couple of months this past summer. And then I visited.
Best summer ever.
Yeah.
Hot girl summer in Antarctica.
What I did last summer. 20 years ago, I went as a student as well. So I've had a couple of trips. It's been fantastic to be, back there, back on the rocks, in the field, feeling like a geologist.
Yeah. And like on the rocks. So again, that concept, when I think of Antarctica as this big blob of ice at the bottom of the world, like there's rocks under there. The ice is an inevitable part, the ice sheets and the glaciers, that is Antarctica, but you were interested in the underneath of that, the rocks.
I mean, it's not good odds for a geologist, right? There's less than 1% outcrop. So I think it's like 0.2%.
Oh my God.
But yeah, you're right, that ice is not floating. It's sitting on a continent, and that continent is 1.7 times the size of Australia. So we expect a really varied geology underneath, and that's what we see in the beautiful radar imagery, in the geophysics. If you were to strip all that ice off, which is several kilometres thick in places, 4 or 5 kilometres thick in places.
5 kilometres of ice.
Yeah. You will see, rift valleys, you'll see mountain ranges like the European Alps, you'll see lakes, all those kind of landforms that we're familiar with in Australia and around the world. They're hidden underneath that ice sheet. But we only see this sort of tantalising glimpse. And so going down as a geologist is, pretty exciting because there's so much unknown. And there's those real key spots where we can actually touch it and sample it.
Oh my God.
And then we can use other data sets to try and further our understanding of what's under the ice. I link it to the geophysics, for example, which can see through that ice sheet.
What does life on an Antarctic research base look like?
Well, so the Australian research stations, they have 3 on the continent, and they're quite big camps, a bit like a mining camp. So you have buildings, brightly coloured buildings. And
are they brightly coloured so you can find them in a blizzard?
That's right.
Oh,
yeah.
stop
I was
it.
just thinking,
They are.
there must be a reason why you say that.
Yep.
Normally you don't comment, oh, the building was green or the building was red, but obviously.
It's a rainbow. So the red shed is typically where the living quarters and the kitchens are. The green store, which is where you find the food stores and so on. The yellow building will be something else like communications. So, yeah, it looks like a mining camp, I would say, maybe a bit prettier.
With an ice sheet behind it.
Yeah. They're built on rock. The Australian ones are built on rock, and day to day they're very comfortable.
So are some bases built on ice?
Other nations have stations on ice, for example, in South Pole, and they're built on usually stilts, I think.
Right.
Yeah.
Do they have trouble with that ice moving?
They do. I believe one of the, I think it's one of the stations that the UK runs is actually separated. It's on a floating piece of ice now. It's on an ice shelf that's...
Is it still operational?
It's still operational at the moment, but I think it's going to be condemned.
That should be the next Ice Age movie. Like, you know, Ice Age movie.
Be a long movie.
Just the Brits off.
Yeah, so day to day on station, it's very comfortable. I mean, there's chefs, there's people looking after you, you've got, great accommodation, cinema, all that, gym.
A cinema?
Yeah.
That's very
This all sounds amazing.
I'm just thinking, poor old Mawson down there.
I know.
Yeah. Well, actually...
Little wooden hut and tinder beans and lost his friends down a crevasse. It's terrible.
But on that point, so there's history there. Like we talk about, time 80 million years ago, but Australians in Antarctica isn't a particularly new thing. Like we've been trying to push the limits there for a while. But you said something to me, and I'm still thinking about it, which is it was an ambitious expedition, right? I think I read one of the most ambitious expeditions in the last 20 years. What you and 26 other scientists did. And you had in your mind that, is it going to be possible to return here, or will there be another time to return here? So you're carrying with you the gravity, you're carrying with you the sentiment of there's a possibility that that it'll be a long time until someone gets to the sites I'm in again. Can you talk that out with me?
Yeah, so we were in this region of the Denman Glacier, which is about 450 kilometres west of Casey. So Casey, Australia has a very nice base there, but we were actually out camping 450 kilometres to the west, and in an area called the Bunga Hills, which is a nice ice-free, lots of rocks around there, ice-free area. And geologists have been to the Bunga Hills and scientists have been to the Bunga Hills previously, and there's been some great work there, but it's very difficult to get there.
How do you get there?
You need to, fly from Casey. So we took a small plane from Casey, a Basler, one of these old aircraft that's been refitted for Antarctic science. And then once we were there, we had helicopter support to get out then into satellite camps and regions and into the rock outcrops.
Wow.
So, yeah, I knew that geologists don't get there very often. And also from my experience working in Antarctic geology, I've worked on other people's collections. I mean, here in Adelaide, you've got Mawson's collections and you can work on them. That's amazing. And they are hundreds of years old. So I was feeling like, we're collecting for us and for the next generation and the next generation. These rocks have so many stories to tell. Let's do our best in terms of what we can collect and the observations we can take in the field and the reporting that all the detail that we can put in, we'll do. Yeah.
That's funny because when I think about the field work you do as an undergrad and you've got your notebook and you're just learning how do you set out your notebook, how do you separate your observations and your interpretations, and I found it a bit of a struggle. I've got a bit of a scatterbrain, but hearing you go, no, what you record and what you collect is really important for future. Yeah,
so important. Yeah, and having that context for the sample. Sometimes you can take someone's sample, but without the context and location or the field photo, I mean, what use is that?
Was
really?
This sample just a pebble?
Yeah.
Or was this in the rock itself? Because if it was a pebble, it could have been scraped off a glacier and dumped there. It might have nothing to do with it. So all those observations are really important.
Yeah, and we were collecting both of those kind of samples. So, we had to be really diligent and it was hard work, I have to say. Going out in the field every day, long days. So we were camped out there for about 2 months.
2 months?
Yeah, and we were sharing, as you said, there was 27 scientists, I think there's 12 different science projects.
Wow.
So we were sharing the logistics across a very broad range of projects. So we couldn't expect to have a helicopter every day or go exactly where we wanted to go every day. So there was that, again, ethos of collaboration. We were all there. Generally, we were there with a common goal. We were there to try and understand the Denman Glacier, how it's changing, the rate that it's changing at the moment, which is fairly significant. And is that unprecedented, or has the Denman Glacier behaved this way in the past? They're the kind of questions. What's the risk in decades, centuries past if this glacier loses mass? And so it was great to be united around that research question. And then we had teams, so we had ice core scientists who were drilling for climate records. We had folks drilling through the ice shelf to get to the ocean and into the sediments below to take samples.
So drilling through ice, then through the ocean onto the floor.
Yeah, getting sediments. Then we had geophysicists up on the ice sheet itself, looking through the ice sheet with their instrumentation, trying to figure out the base of the glacier, what it looks like, the properties of the deep earth. And then obviously geologists were going to the rocks and sampling what's on the sides of the glacier, and then how can we predict what's underneath it. Who else? We had people looking at birds, people looking at moss, people looking at lakes. So
birds, moss, and lakes in Antarctica.
Yeah.
Get out of here. That's awesome.
So it was very multidisciplinary.
Yeah.
And just, seeing how those projects work together, just like scientifically, but also logistically. Like day to day is really interesting. And so where we could overlap in terms of space, we would. So we would go out with a geophysicist, for example, or we could go out with the Moss team if they were looking in a particular area that had cool rocks as well.
I've got to say that surely the samples that the Moss team takes are going to be smaller than and lighter than the geologists.
Yeah, I mean,
in that helicopter's struggling to lift off. Oh, the geologists are on the side again.
The faces of the helicopter engineers who are unloading the packs at the end of the day are just like, you guys, you could just see them. I mean, you can't talk because it's so noisy, but you just see them rolling their eyes as they pull these backpacks out.
That's awesome.
Yeah.
So what's the relationship between the bedrock and the ice itself? Is there a kind of a connection to those things, or are they kind of just two things that happen to go their own way?
And bedrock being the top of the landscape, if you were to remove the ice off the glacier, what's next?
Yeah, so Antarctic ice, I mean, it's not just sitting there passively doing its thing. It's very much coupled to and linked with the geology and the bedrock underneath. So what's interesting is these fast-flowing glaciers, they're often actually sitting on top of geological contacts or fault zones, or there's something in the tectonics that has concentrated the ice to be flowing in that location. So that adds a sort of a high-level control over the ice sheet, which is really cool. Right. So why is the ice flowing fast here? What's happening underneath? And usually at first order there's a geological control. And that's the case in the Denman. So it's actually a sedimentary basin that we think was correlated with the Perth Basin of Western Australia. So it formed initially in the Permian about 250 million years ago. And so it's got sedimentary rocks underneath it. And then either side it's got fault scarps. So it's pulled apart, this basin. It's got high-grade metamorphic rocks and igneous rocks on both sides and a sedimentary basin in the middle. And of course, those sedimentary basin rocks are much more erosive. So the ice sheet likes to...
They're more easily eroded, you mean?
More easily
eroded
compared to the granites and the metamorphic rocks on either side, which are pushed up relative to the basin. So the ice is concentrated in there and then it can flow. The sedimentary rocks have porosity, so that allows water to circulate.
So is there water coming from glacial melt into those sedimentary rocks underneath the glacier?
It's probably not coming. It's not coming from the top down, but we've actually got melting at the bottom. So, yeah.
Do you mean the glacier doesn't just sort of does it sort of slide on a mushy kind of melty
that
layer?
Big fat Denman Glacier is capable of sliding.
Yes, it's sliding at the base, and that's the problem actually with the Denman Glacier in that it's sliding. It's probably got a lot of subglacial water below it pumping through this sedimentary basin. We know the heat flow in that area is quite variable. And
what do you mean by heat flow, Jackie?
So there's a natural heat coming from the earth, and that's coming from the centre of the earth, which has been that way since it was formed. But it's also coming from the crust. So the crust, different rocks have different radioactive elements in them, and they are naturally decaying and giving off heat. So A
small amount.
A small amount.
Surely.
It's small, but when you've got an ice sheet on, which is a good insulator, sitting on top, those variations in that crustal component of heat is actually really important.
Wow.
So you can have certain parts that are actually getting up to their melting point and melting.
The rock is melting?
The ice sheet is melting from that variability in heat.
Yeah.
And so certain patches are melting more than others, are creating water, and that makes it more slippery. And the other thing about the Denman is...
More questions?
Yeah.
Sorry, continue.
Well, the other thing about the Denman is, unfortunately, for us, the slope of the Denman Glacier, the geology underneath, is actually sloping back. So we call that retrograde slope. So if the ice sheet does become unstable and that warm ocean water can get up underneath it, then it can get to a certain point where it keeps retreating and the ice loss is sort of a feedback there where you lose ice and that creates more space for water to get underneath and you lose more.
So do you mean, when you say retrograde, do you mean that the shape of the base of it is tilted towards the internal part of the continent?
Yes.
So it's like if it gets over that lip,
yes.
Is that what you mean?
Yes.
Then it will fill the bottom part of it and accelerate the melting of the glacier.
Yeah, the ocean water is actually warm.
How wide is the glacier? What sort of size are we talking about?
Yeah, I think we're talking maybe 15 or so kilometres wide.
Right.
There's another glacier next door, the Scott Glacier, and they're kind of part of the same system, feeding into the same ice shelf. And it goes for maybe 100 or so kilometres inland. And it's one of these glaciers it has retreated about 5 kilometres in the last 2 decades, so it's retreating and it's accelerating in that time. But how is that normal? Is that unprecedented?
Yeah.
I mean, they're kind of questions that we're there to ask, and particularly because it's retrograde. You know, if it is retreating fast, then that's a problem because it's actually holding back about 1.5 metres of sea level rise equivalent of ice. So if all that ice was to go, that's the impact on the global ocean.
So on top of that,
yeah,
the fact that there's a glacier there going slowly, does that glacier connect back to the main ice sheet itself?
Yes.
So is that also
the
part
main
of the
ice
kind
sheet,
of dynamics of it?
Yeah, the main ice sheet's sitting there, and then these fast-flowing parts around the perimeter are called the glaciers, the glacial systems. That's where most of the outflow of the ice is coming and then eventually carving off what we call the grounding zone, where the ice meets the edge of the continent and then starts to float, the grounding zone. That's when icebergs carve off and off they go. So those fast-flowing parts of the glacier, of the ice sheet, are called glaciers. But the whole ice sheet is all moving due to gravity slowly.
How much snow happens down there to replace this ice?
Yeah, good question. I don't really know.
It's a pretty dry continent, right?
It is dry. The accumulation rate is important though because obviously you're adding mass and losing mass. So it's that mass balance that we have to worry about, you know, how much we're gaining and how much we're losing. And so then people that look at using satellites usually are looking at the change in the flux between what we're gaining and losing at any one time. So they're the things we have to worry about. But yeah, the Denman, I guess it's kind of a canary in the coal mine almost, like for East Antarctica. It's one of these glaciers that we're worried about because of the impact of what could happen if it was to retreat quite quickly and the fact that it's showing signs of retreat. And we know that, well, we think it's not unprecedented. It has happened in the past. So in the Pliocene, it's quite a warm period, about 3 million years ago, where people look at that as a bit of an analogue of where we're going in terms of our climate and carbon dioxide levels. And we think that these glaciers in this region were retreated quite significantly in that time. So it's probably happened in the past, but we don't really know with the Denman. So
can you tell that sort of information from looking at those ice from the cores and the sediment off the on the what am I trying to say? Off what would have been the beach of Antarctica, and if you drill in those sediments there, you can tell the sedimentary changes to tell you what was going on.
Sediments, yeah. So part of the data set that's used to look at retreat is what erosion was happening in the hinterland. So you can use geophysics to say, okay, what erosion patterns can we see underneath the ice sheet today that suggests that the ice sheet was retreated and eroding further back. So that's what's been done in this region. And the other thing is to couple it, like you said, to the marine record. So as the ice sheet erodes and chews on that rock, it dumps it out in the ocean. And so we can actually take sediment cores, which go back in time, and have a look at what sort of material was being dumped off from these glaciers. Both the volume and the size of the class can tell you something about how the ice sheet was behaving, but also if we can get kind of technical and look at the age range of the different minerals in that core, we can understand, okay, exactly which rocks was the ice sheet actually chewing on at the time. And that's something that we're going to be working on, is if we can understand the geology in the region, we can then predict if the ice sheet was at a certain location in time and was chewing on those rocks, what signature should we see in the marine core? So that's something we'll be working on, trying to understand the fingerprint, the chemical fingerprint around the Denman of the different types of rocks. And then we can play with ice sheet models and say, okay, if the ice was retreated a certain amount, what sort of rocks would we expect it to be eroding? And then we can look at the marine record.
Yeah.
Yeah, and figure it out. So that's kind of a nice relationship between the terrestrial and the marine record that we can use to understand the ice sheet in the past.
Fantastic. And that's a body of work coming up or in progress?
Yeah, that's what we're working on. We've started work on that in the Denman region by looking at an old IODP hole, so a very long hole that was drilled in the 70s actually, which hasn't really been worked on, that goes through this Pliocene warm period. So we're looking at the moment at what that core can tell us. But the Australian program is going back to this Denman region in 2025, and they're looking to drill new sediment cores.
Right.
And so we'll discover more about how the ice sheets behaved in the past, and then link that to what we find with all the samples we've brought back about the geology of the Denman, which is quite variable. We know that it's quite different one side of the Denman Glacier to the other.
Right.
And we also expect some differences inland. So if we can tag that geology with its fingerprints, and then we can look for how the ice sheet's changed.
Incredible. Who's working on these now? Are you going to be beavering away on the chemistry and things like that of those rocks, or have you got other people you're working with?
Yeah, we're going to work as a team because we've brought back 1,000 kilos.
Oh, my A ton.
Yeah. A ton of.
You brought back a ton of rock from Antarctica.
We had a
I
permit.
guess at the scale of a continent, a ton is not a huge amount of rock.
For a helicopter.
For a helicopter, I know. We had a permit for 1,000 kilos, and I really didn't think we'd get there, but we did.
Well done.
So
did you wash your? Sorry, I saw a photo on Twitter, or whatever. I saw a photo on that platform, and it was, I think, your washing hanging out, and then your rocks hanging out.
Yes.
Did you
We
Did you
did
hand
have to
wash?
hand wash each rock, because we had to get off the lichen and any soil, and just for quarantine purposes.
Yeah, of
so
course.
that was a labour of love. We got more discerning with which rocks we chose towards the end of the season. No lichen. We were not liking the lichen.
Yeah.
It's very hard to get off.
Sad North scientists.
Yeah. So we'll be working as a team. So I went with a colleague, Jack Mulder, who's here in the University of Adelaide, who'll be working on me with this project, and we've got some students involved. Yeah, it's going to be a big collaborative project. I think we worked out, look, we've got 7 or 8 projects worth of stuff in this sample set. And of course, like these rocks, they're going to last a long time. So who knows what else they'll be used for in the future.
Incredible.
Yeah.
I've got another question now, a little bit off topic, but related to what you're talking about there. You know, you've had a lot of experience now with students, and particularly PhD students, and it sounds like you've got a whole gang of them coming on board soon. And your work at University of Tasmania has a lot to do with students and their kind of trials and tribulations of their process. I was just wondering if you would mind sharing with us some sort of like Jackie's hot tips for how to survive your PhD sort of thing, you know?
Yeah, that's a good one. I think they're very individual journeys, but it really is a journey. Yeah. I think you've just got to really want to do it. Hey, like it's not a job to take lightly, and it really is a job. It's exciting and it's a journey, but it's also a job, so you have to really want to do it. I think. Like sometimes I say to students who are having a hard time, it's like you don't have to. You could actually. Maybe this is the wrong thing to say from the university perspective, but
you're here as Jackie. That's okay.
From a personal perspective.
People matter.
This is a big chunk of your life, and you know maybe it's not the right time. Maybe it'll be the right time for you another time, or maybe it's just not for you. You know, a lot goes on, and students are often in their early 20s, and there's a lot going on in life.
There's a lot going on in the early 20s, can vouch.
Like, you know, you're usually like meeting, you know, potentially you're meeting a partner and you're moving out, and there's just a lot going on. So you got to want to do it, I think, and finding the right. I actually think, like, I like rocks, but people are cooler than rocks, and also more, I think, more integral. Like if you find the right team, actually sometimes doesn't matter on the project necessarily. It's key to find the right people around you to support you, have a really good relationship with the supervisor in terms of the expectations of what you're doing, why you're doing it, what you're getting out of it, and that communication. I think when I've seen things go wrong, it's that mismatch of expectations, poor communication, which is challenging always, but like something to work on.
Well, I mean, you see that in the workplace, or whatever. That's just human nature, and things can go wrong.
Yeah.
But in this case, because it's a almost like quite a solitary exercise as well. So there's something about that soul burden. Whereas I guess if you're working in a team and something kind of goes wrong, well, then there's a team to sort of bounce stuff on. We can work as a team, and you can fall back on that. But this is a really solitary. Oh well,
it can be. So maybe finding that team. Like even if it's not a team project, but just finding your people to support you, and you can make it team. Like collaborating is my favourite thing, and I think I learned that during my PhD that you can collaborate. It doesn't have to be a solitary thing, and that's something to be enjoyed and can hold you in good stead when things get rough.
Yeah, that's one thing that I think.
Did you say when?
Oh no! Don't you both look at
me. Surely my PhD project will be different.
Oh my God, I'm scared. That's definitely one thing I'm learning about science, right, is that the secrets to the universe and the secrets of how nature works don't just beautifully unroll like this carpet tapestry for us to sort of peruse. It's work and it's people, right? It is a human behind every new little pin of scientific knowledge that eventually builds up into something meaningful. And your point about teams, I think we're attracted to the idea of assigning one figure or one person, or one research paper, but really like it's a bit of a slog. It's a beautiful slog, but it is a slog to make that research work. And a PhD project is just one drop in the ocean, but it's your drop, so it matters.
Yeah, no, it does, and it's exciting. Like, it's exciting, but I think that team element is quite key.
Yeah.
Have the people that can.
Well, it's age old, isn't it? People matter. It matters who you surround yourself with.
I often think of like the science, like even in the field, how will I represent these observations? And two people will represent them differently. I think that's, with the PhD, you can have the facts in front of you, but you're still going to have, depends on the person. It is like an interesting human element to science. We're not going to interpret it the same way. We're not going to write the same papers. We're not going to write the same thesis. So your voice in that science is key, actually. So that's cool. So your contribution is quite unique. It wouldn't be made by anyone else, even with the same data set. It'd be a different story.
Amazing. Thank you so much for taking the time, Jackie. Incredible that we're looking at someone who deeply knows there's still questions to be answered about that big white thing at the bottom of the earth. So thanks so much for your time.
Pleasure.
Thanks.